Hi, I'm Nico Ritschel, and I'm going to present to you today about how basically, as he already introduced, how guided decomposition can help end users write larger block-based programs, or whether it can. And this is work together with my supervisors, Ron Garcia, who's in the room, Reed Holmes, as well as Philippe Franchetti and David C. Shepard from the Virginia Commonwealth University in the US. So I don't think I need to give a big introduction to block-based programming, since it's quite popular and has definitely arrived in the mainstream, I would say, at least of computer science education. So if anybody is unfamiliar, here's some of the most essential features that you should keep in mind when thinking about them. So in block-based languages, you get this like jigsaw puzzle-like visualization of the program syntax. And you can do this syntax-directed drag and drop editing, where you basically pick syntactical fragments from a drawer and you place them on the canvas and you attach them to each other. And there are some other features that might not be immediately obvious from looking at this screenshot, which are that in block-based languages, typically, it's always like a bit of there are some exceptions, but typically all programs that are visually composable so that you can attach to each other syntactically are also valid, also on this level that you can compile them. So there might also be some sort of type checking already going on based on the block shape and so on in some languages. And also block-based programs try to be readable as sort of natural language on that sense of a best effort, I would say. So like, it's not like natural language processing, like it's not like you can write whatever you want, but it's approaching, like it's trying to avoid abstract program syntax and going more for sort of intuitive either icons or text that represent the semantics of the program. And another important feature is that blocks, and that is sort of distinguishes them from a lot of other visual languages, is that they are still quite close to actual text. So you can, for example, in this program, sort of strip away the blocks quite easily, replace this by a text-based version, or vice versa. You can turn a text-based program into blocks. And this transition can, especially in the context of education, help people transition from like blocks to text quite easily. But we're not going to talk about education today. Like, this is not a Splash E talk. We're going to talk about end users. And so end user programming is starting to adopt blocks. It's a relatively recent trend, but even now there are quite a few block-based languages where you can program robots, for example, in industry, or where you can automate your home with blocks. And some of the reasons why this is quite like a trend and quite popular with industrial users is that block-based environments are definitely cheaper to build than custom ones. So you don't start from scratch, but you start from some frameworks that exist, and it's quite easy to build up and basically take your own language and sort of stick it into the block-based syntax. And studies have shown in some of these applications that typically blocks are easier to learn and easier to use for beginners than traditional like tools that would be used in the domain. And also there's this bit more of a gamble, you could say, or a bit more of this assumption that if everybody is using blocks in this end user space, there might also be this effect of sort of standardization where if you've seen a block-based language, it might be easy to transition to a different block-based language with a slightly different sort of underlying language, but the same way to manipulate programs and the same kind of model to think about them. But end users are not students, and that's important to keep in mind. So end users do not have the goal to learn programming. They want to complete a specific task at hand, and they do not care about sort of graduating from blocks at any point into a general purpose language. And they might use basically the same language for their very first contact with programming that they ever have, all the way until actually solving that real production task that they eventually want to solve. And this task might be quite a bit larger than the very first program that they write, quite obviously. And that raises the question, how does block-based programming scale to these like larger programs? And again, like large is in quotations here because we're not talking about enterprise Java size code, but we're talking about like maybe dozens or hundreds of lines of code at most, like something that an end user can still manage, where you don't have to reason about some other questions that are not directly related to code, like software architecture and so on. But again, even if we look at this size of code, I would argue the sort of the user friendliness of this becomes slowly questionable. And this is not like the largest you could find here. And you can quickly see that this turns into this somewhat colorful, almost like a bit artistic, like mess of code that is, I would argue, at best as easy to read as the text would be that is inside these blocks if you would just use syntax highlighting. So unfortunately, there isn't a lot of data actually available on this that is really reliable. There are repositories of block-based code in the wild, but the problem is they are kind of a mix of some end-user code, some student code, maybe some kids code, and so on. But one thing that you can find from there sort of overall is that people don't really use functions or like any other method that block-based languages would provide to decompose their programs. And you quite often find this so-called long method code smell. Like often, like method is maybe a bit misleading here, but like this idea of you have a long chunk of code, like you can see on the left, where you have basically one big connected component that is just linear statements without any decomposition, and you just have your program basically written in this kind of spaghetti code style. And that raises the question, so why don't users of blocks decompose their programs? Because there are decomposition mechanisms offered, but maybe it's worth looking at these mechanisms to understand that a bit better. So if you look at, for example, let's stick with Scratch, since it's the most popular language, you have support for functions. And functions are, they're called custom blocks, so it's just kind of a renaming of the feature to make it slightly more intuitive for non-programmers. And you have some simplifications, typically, like maybe you don't have return values, like some languages support them, but not all of them. Some support parameters, some don't. But there are things that block-based languages don't do, and that basically everything up to that point, any other language could have done as well. But some things that blocks could inherently be helpful with are not actually done by them. So they do not attempt at all to like represent scope in any way that is helpful for guiding the user. They don't make any attempt in actually guiding or supporting users in how to structure their programs. And often they don't even provide feedback in case of errors, like in this example here, where you could take this threshold local variable that is defined within this function and just drag it anywhere else, and it fits in there. And this is like, for any like experienced programmer, you would look at this and you're like, this is nonsensical code. Like this is, I don't know, at best undefined behavior, but there's no feedback at all to an end user. And even in some languages where they try to have feedback, it's at most like a sort of an exclamation mark, check this or so, but there's no effort to at all prevent this from happening or represent this visually in a more intuitive manner. But there's something else that is also holding end users back, which is the question of when do you actually decompose a program? Like right from the start, when you just have one block on screen, you immediately start thinking about decomposition when your code grows, or like when is the right point to actually think about, maybe I should start using functions or sort of changing my code. And this is obviously not a new question. This is a question that is quite challenging even for professional programmers. And we might argue that size is actually not the right metric for this, but what is the right metric? Is it like you want to think about sort of abstraction? You want to think about operations that you can try to abstract into a function call? Do you want to maybe think about if you reuse code? But all of these questions are questions that are even hard questions for professional developers, and definitely so for end users that have no experience with this. And this is their very first time ever using a block-based or any programming language. And I would argue that this skill of effectively coming up with a way to decompose your program, especially while you're writing it, it's a bit of a different question when we talk about refactoring your code later on, which is another thing that is basically unsupported by blocks nowadays. But even while doing this while writing the code is definitely a non-trivial skill that many of us might have, but that end users are unlikely to have in practice. So why do existing systems not just do more to support end users? So there are some factors, and keep in mind, blocks are designed for education. So educational programs are often short code snippets where it's just about learning a specific like programming feature, basically. And often this code is quite short and you don't even need decomposition. Also, often in this educational context, you have more time, you have practice, you have guidance quite often. Like, I mean, there are sort of these tutorials that are sort of all like self-taught, but quite often you have a sort of some instructor that basically is teaching this kind of course and is giving you guidance on how to use these features. And quite often also by the time you really run into this issue in this education space, you have graduated from blocks already, and you're already in a general purpose language. And at that point, that's like blocks are out of the picture. So block-based programming is designed for students and not end users in its current state. But it is used for end user programming, and that is a bit of a mismatch. So can blocks do more to support end users? And we were asking the questions, can they guide end users in reasonably decomposing programs? And ideally not in a way like here where you just nag them and be like, hey, your program has 100 lines of code, fix this somehow. Or like, you want to have a way that is more natural for them. Can you provide a better interface for actually reading and navigating decomposed programs? And our hypothesis for this work is that, yes, we can, not necessarily in a very general purpose context, but that's not necessary because, again, we're talking about end users that usually have a specific task in mind that is within a certain domain. And if you focus on this domain, then it becomes quite like a lot more sort of within the realm of the possible to actually support them at decomposition. So in this work, we're going to look at one specific domain, which is mobile robots. So you have a robot with like this sort of movable bottom part that just can drive around in a room. And then you have a robot arm that is quite sort of all the standard industrial robot arm mechanisms. There are languages for, especially for this programming robot arm part, already available. And the reason why this domain is quite useful for us is that programs very quickly tend to look like this. Even with some, we are already providing abstraction, for example, for moving from one place to another. We say the robot can under the hood do, I don't know, machine learning, we don't care, like some mechanism to basically learn how to go from A to B. That's not something that end users might want to reason about, but even then, there is a lot going on in a program that is conceptually easy. It's all just pick up things up, move them somewhere, drop them off, but the programs just become large because there are a lot of operations going on. And so we built an environment that is focused on mobile robot programming and that provides some features to end users, which are a more domain-specific way of representing functions and guidance on how to structure programs within this domain. And also some more support on this like block-based language on this more visual level, in a sense, or like in this environment level for actually navigating structured programs. So this is a screenshot of the environment that we built with some sample program. And the first thing you are probably going to spot immediately here is that we built an environment that has two programming canvases that are entirely like their own canvas. And one is specifically meant for using functions, for basically composing them, for sequencing function calls, and one for actually like defining the function body. And these two environments have completely different like syntaxes available. That's a feature that is inherent to block-based programming, is that you can control what users have available at any point as they're writing code. And we are making use of that to provide the syntax that basically pushes them towards decomposition. And another feature that we get almost for free with this idea, so the flow is in a sense you select a function on the left side and then you get the definition on the right side. You end up with this support for scoping almost like for free because the functions exist in these separate canvases and there's no dragging blocks from one function to another. You just intuitively get this idea of anything that is defined within the function stays within the function. We're also making use of some domain-specific properties. So these canvases in the context of mobile robot programming align quite nicely with this intuition of the robot is moving on sort of a more high level between different stations, and it then is doing some more localized work there. And this is kind of represented here, where on the left we have these movements between stations that are connected to the function calls, and that actually, because they're connected, basically can happen implicitly. We say whenever we move to a station to do work, to have a function call, we also move there in like the same block. And then the actual work that gets defined on the right side of the screen. And so we in our paper, we actually evaluated this kind of environment, and we compared it to a traditional environment, which is more or less like sort of the state of the art of what you would expect in a block-based language, where you just have like this, what we've already seen before, this kind of custom block style of defining functions that you can do in any way or shape that you prefer. And we compared these two, and since unfortunately because of COVID and also for sort of, it's simpler to do this without having a real robot and having to basically explain users how to interact with the robot as well. We decided to do this as an online experiment where we use a simulator that is basically replicating the essence of like a mobile robot, where you have this little robot and that can move from one station to another and grab things and drop them off somewhere for our study. And we conducted this study. We used Amazon mTurk. We recruited 92 participants, and we randomly split them into two groups. So we have like a controlled experiment set up here. And we have our one group that uses the traditional environment and one group that uses our guided environment. And so the overall flow, it looks basically like this. I'm going to go through this in detail. Don't worry, but basically we taught the users with 3 tutorials, which we try to keep as close and similar to basically between the two groups as possible. It's not possible to have them exactly identical, like it's the same tasks, but the instructions obviously change a bit based on the environment that you're using. And then we have 3 completely identical tasks that we ask them to perform using the environments. And so what we found was, so during the tutorials, we, as I already said, like we try to keep these as similar as possible. But we also focused on specifically introducing users to the idea of using functions and to how to use functions, how to reuse code, in the hope that that would encourage them to actually use them and make sure that they don't sort of miss this feature entirely and just never open the bottom drawer because they've never seen this feature. And then for the tasks, so we started with a relatively simple warm-up task where you don't really need composition. That is quite simple. It's like 10 blocks of code, roughly, to just move some blocks around to basically get them accustomed to the environment and the idea of decomposing, the idea of writing programs in this. It is also interesting because it's a bit of a check, sort of a sanity check. Does our environment work in this context where you have a small program where decomposition isn't necessary? Like that might our approach actually be harmful in this case because it sort of pushes them to overcompose their programs. Then we also have a second task, and this task is longer and it's designed to be as obvious as possible in a sense that there's a lot of redundancy going on and how you could decompose it. So we have multiple workstations and the robot does work on each of these stations, and the work is basically identical. Like it's identical between 2 of the stations, and then it's some trivial thing like, oh, you have to switch left and right. But it's very obvious that you can, especially for the first 2 stations, literally just use the same function twice at a different station. And we specifically designed this task to see for the users in the sort of the traditional environment, like, are they using decomposition in this extreme case where it's as easy for them as possible? And then we designed a third task that is maybe a bit more natural, where the robot does work sort of between stations and moves blocks between different stations, and where the redundancy and the reusability of code is less obvious to them. We designed all of this to basically ask a few research questions that we look at in detail in the paper. So for the traditional environment, we are looking at how do end users decompose their programs when they have all the freedom available, especially looking at that there's not so much data available on the question of how end users decompose programs. And we're also asking the how here is in parentheses because do they decompose their programs at all? We also ask, does the decomposition actually affect their performance? And then for the environment that we built, we are asking, how do end users decompose programs there when they have the guided decomposition? And finally, sort of across both environments in comparison, does the guided decomposition help them and affect their performance while solving the tasks that we gave them? So let's start with the first questions about the traditional environment. So what we found is that maybe kind of in line with what we've seen with the data in the wild, many participants have ignored functions altogether. So for the second task, like again, the one where decomposition was very sort of on the nose how you could decompose programs, we still found that only 42% decomposed their programs based on this like per station style, and then we have 18% more that used some other pattern that is not really following any, like they just try to decompose their programs but didn't really follow any clear pattern that we could recognize in between them. And for the third task, where it's less obvious how to decompose programs, we found that only 28% of participants used any decomposition. All the other ones basically wrote programs that look like the one you see here on the left, where they just basically have like dozens of blocks in this style going down. And for task 3, we also found that participants who did try to decompose their programs, so likely ones that would, like similar to the in task 2 to the group that has no discernible pattern, users struggled with actually like using functions effectively. So in this example, we have, for example, move instructions within a function, which means that even though the user is trying to do the right thing, it's like move to station A, do something, and then move to station C and do the same thing. It doesn't actually work that way because there is this movement back to station A already inside their function. So they are in some sense trying to reuse code, but they fail to do that because they don't get any support from the environment. That's at least our argument. Oops. We also found that, coming to research question 2, that participants that use decomposition, again, like in the non-guided environment, so where they had all the freedom to decompose programs, they performed better across the longer tasks. So we saw that for task 2, 83% of these participants that used any form of decomposition, we're like sort of merging all the different types here together, solved this task versus only 71 overall. And we saw that 77 for task 3 were able to solve it versus 54 overall. This comes with the caveat that like this might look like, oh, functions always help, but there is the causality between the two here is a bit unclear. Like it could be that functions caused success here, like that functions helped the end users, but it could also be that end users that understood programming better, again, like these are end users, like we pre-filtered them that they're not programmers, but it might be that that basically their better understanding of the system made them use functions as like a more advanced feature. For the guided environment, we found, somewhat unsurprisingly to us, that decomposition was quite uniform, following the style that the guidance basically pushed onto the end users, and following this like between stations work on the one side and then at station work like within the function style. We did, however, and that's kind of surprised us, find that that our participants very rarely reused code even in this environment. Like again, even in this case where we have the two same the same work done on 2 stations, and they could have literally just dragged the same block in there twice, they decided to just redefine this from scratch. And like even though it's nicer to read, in the end they cost themselves a lot more work and potentially wrote less maintainable software in the end, even though maintainability was not like a goal that we specifically gave to them. We did also find that our environment isn't perfect. Like it leads to over decomposition for some tasks. So sometimes you have effects like this one here, where you have very short functions and a lot of function calls happening. So that made it particularly interesting when I'm next going to come to the performance improvement. So this was a factor where I could say, did this affect the performance negatively? However, when we look at our last research question and comparing the performance, we see that for the first task, performance is about equal. It's sort of, again, like the sanity check. Okay, our environment didn't hurt in this case. But for the other tasks, we see this quite substantial difference in success rate. So we see for the second task, 71 versus 91% success rate. And for the third task, even 54% versus 83% success rate in solving the task. And on the right side, we see box plots of how much time participants spent on each task and each tutorial. And while here if the results aren't as sort of drastic and immediately obvious, we still see that the times are sort of within the same ballpark, somewhat shorter, and especially, and that was a concern that we also had, not much longer, since you could argue that more decomposition takes longer to think about or reason about, but we found actually the opposite, that the time spent on these tasks was actually shorter for our environment. So we conclude that guided decomposition made them solve tasks faster and more successful. So coming back to our question in the title of the paper, can guided decomposition help end users write larger block-based programs? With this context given that we're conducting an experiment on mobile robots, we conclude that yes, in this case, our environment did help users of the block-based environment. Now, we admit that applying this to a different use case or a different domain is a non-trivial effort. Again, if you look at this environment, there are a lot of challenges there where you, like in this case, we have this sort of two-level structure. In other domains, it might not be as obvious what the right structure design is, or like how many levels you need, how the ideal sort of design for decomposition here is. However, again, like as the people who design these environments, we are usually the ones that have a better understanding of, like, maybe not a better understanding of the domain, but a better understanding of how to translate domain-specific knowledge into programming features or into programming language design. So this is something that we argue can be quite, like, yeah, it's like an under-addressed issue and an effort that can be paid off to actually put this extra thought into how to adapt block-based languages, or you could even argue any language, but we focus on block-based languages into this domain. That was our work. I don't look at the time. Looks like somewhat reasonable. And yeah, thank you for listening. And you can scan the QR code if you want to play around with our. We have like the sort of the whole experiment set up. Like you can play around with these tasks in the environment. You can also just follow the link here. And yeah, now I'm happy to take your questions. Thank you. If the microphone is charged, working now.
We have a question. The mic has been charging during the talk. It was not charged before, so.
This is on.
Okay.
Yeah, it's working. Okay.
Do you have a question?
Yeah.
No. Half some percent of the mic did not come with me. Sorry. It's like, this used to be bigger.
Oh, thanks. Okay. Yeah, we discussed it before, so it's nice work. One thing that I was wondering, did you also track copy-paste kind of behavior between the different stacks or between the different implementations and see if that worked?
So we did. So when we say that there wasn't a lot of reuse, that typically means that participants did copy and paste code, or like we didn't track whether they copy and pasted it sort of with the copy and paste like action, or if they actually rewrote it from the beginning. But yeah, like basically we are talking about something that is virtually the result is the same as a copy and pasting of the code when we talk about not reusing code. So they.
Yeah.
Like they didn't just reuse the same program. They rewrote it or basically copy and pasted it over. So.
So on the same lines, did you kind of track if people were using a scratchpad or something for writing these sequences of instructions? Because it seems to me that for some of these instructions where you're translating and then doing some operations, some kind of demonstration, programming by demonstration might be kind of very helpful. So maybe if people are actually like scratch padding on a paper, like do this and then this, and then kind of writing it digitally, then one of like a good programming environment might be to replicate that on the.
So we didn't like since this was an online experiment, like we didn't ask them if they used external help. That would have been interesting to see. One thing that we did, however, see, so I would argue that probably there wasn't really that much need for it, because the simulator here on the right, this wasn't like a one-shot experiment where they can only run this once and see if it's right. We basically allowed them to try as often as they want and reset, and so they can try out partial programs as often as they want to kind of debug their code and see until it works. They could keep working on this. So, I mean, maybe they still used additional like sort of on paper methods, but I would argue that probably a lot of them just kept like we saw a lot of trial and error. Like when we look at our actual sort of data, we see that a lot of them retried several times throughout the experiment.
So how the program evolved would be interesting, like to kind of analyze and see.
yeah, so the question, or like the comment was that it would be interesting to see how the programs evolved. And yeah, I agree. It would be interesting to kind of understand their thinking better, to see how the different intermediate versions looked. Yeah, I agree. Something
Maybe one last question while you get set up, Yalta. Yep, one last quick question.
So what I was wondering is what your descriptions of the problems looked like. Like, were they kind of close to the code that you were expecting people to write? Because especially for this example, I would kind of imagine giving people a table of, like in this combination of station and whatnot, do left, right, and then otherwise right, left. But block-based languages are really bad at like.
You were referring to the second task, I think, or was that basically like this one sort of? I mean,
yeah, and I mean the long sort of code, with all the various left right thingies.
Yeah, like again, like in some sense we picked this one also to underline the redundancy, to maybe nudge them into like, this is quite a bit of code you need to write to do this like stacking, or these stacking operations. Like there's a lot of things going on in each of these subtasks. That basically this short description move the stack to the right translates into a lot of individual steps. That's kind of intentional in the design there. Yeah, I would say we try to keep these task descriptions sort of on this level of where they would probably see them in a real application. Like, I mean, I would argue maybe even this like, here's the result we expect might already be something that is more vague in reality, but I feel like giving them more details on like, here are the individual steps, that's not likely to be something that they would encounter in like, if they would use this in practice, like on a real task.
Okay, let's thank you.